case, we're plastics consultants, and we are very heavily involved in developing new products, and plastics is a pretty substantial part of. And this video is really directed at those who don't know a lot about plastics and just going through some of the basic fundamentals to give you a general overview of what choices you've got and what issues are relevant. Now, firstly, I'll start off with a sieve test to say, right, you want to make something out of plastic. Here, the sieve test is basically designed to try and sieve out the sorts of issues that are important in your particular case. And in this case, let's get started with, firstly, is the application inside or outside? Now, if it's outside, you've got ultraviolet involved and weather, rain, whatever, but UV is usually the big issue. Not as big an issue in places like the UK, parts of Europe and other places where they really don't get the heavy sun issues that you get in places like America and Australia, where the sun does shine. Ultraviolet will break things down very badly, and therefore, as soon as you're outside, your choices sort of suddenly go down, because you're obliged to use a product that has, as a plastic, has intrinsically good weathering resistance. I mean, things like acrylics and other products lend themselves to that, and products that have been pigmented and loaded with UV stabilizers to try and stop them from breaking down. And when we say break down, what we're defining as the surface chalking, the material cracking, the clearer the material, the more light that gets through and into the depth of it, the more it will disintegrate. I mean, you say, for example, take a clear bottle that was intended for use inside and expose it to sunlight, and the thing will often just completely craze with time. You just grab hold of it and you just crack into a mile of pieces. So after we've been through the UV test, we go to the temperature issue. Now, there are extremes of hot and cold. If a plastic gets very cold, as the cooler it gets, the poorer the impact strength will be, and that can be quite an issue with some things. And initially, you probably don't always think about what are the extremes of use of the product. That is, what conditions will it wind up in its working life to have to face up to. So if we had something outside again exposed to the weather, in some climates it may get to minus 10, 20. At that temperature, a hell of a lot of plastic's very brittle. So you need to be quite conscious of this. On the other side of the equation, on the other side of the equation, with heat, we've got two common effects there. One is the product can yellow quite badly just through heat. Putting UV aside, the heat alone can yellow some things. Also, the heat can take a product in extremes past its normal heat distortion point, where it'll start to sort of droop. And also, depending on its coefficient of expansion, it can expand at quite often a vastly different rate to, say, if it was fixed to a metal or masonry surface, the thing would start to ripple and crumple because it's trying to expand and the surface under it doesn't expand at the same rate. So you get the case of differential coefficient of expansion, where the two different materials span different rates, and if they're fixed together, you can get all sorts of problems. So also temperature can degrade plastics in the sense that their strength just gradually wilts away with continual high temperatures. So having worked through those two, then we get to the issue of fire and issues related to flame. Is there a requirement for the product to be fire resistant? And then be conscious of the fact there's a whole pile of different rules and regulations and standards relating to this. So you might want arcing resistance, you might want the thing to be basically non-burning. Well, that sort of really puts the pressure on. And it depends on what country you're in as to what rules are applicable. And then, of course, if it does actually burn, what are the products of combustion? And some plastics with fire retardants in them will sort of kill off the poor souls that happen to be around when they burn, because the products of combustion are pretty nasty. So that's an issue you've got to be conscious of. Fire resistance can be relative to the particular type of plastic. Some plastics don't propagate flame, others do, and then you've got the next option of putting fillers and additives in to try and make something retardant, or to get a degree of retardancy that fits the appropriate standard in question. So the next issue is chemical resistance. Does the material need to resist everything from water to acid to all sorts of things that it may come in contact with? There the question is the chemical in question, the concentration of that chemical, and the temperature. And usually there are tables around for most materials, so you can get a measure of that. Then we get the other issues, other strength issues, apart from impact we've spoken about, flexural strength, wear resistance, in some cases very important for surface wear, the actual wear resistance, which again is measurable in terms of things like Tabor abrasion tests and various other things. And that sort of takes you through most of the key parameters involved. Be conscious that the more exotic the requirements for your material, usually the higher the price. It's the simple rule of thumb formula. If you don't need any exotic properties, well then, you're down the cheap end of the track. As soon as you start needing exotic properties, you have to pay more for it. So then let's move on to the next of the two different types of plastics groups. One thermoset, one thermoplastic. Thermoplastic is something that you can heat up, form a shape, cool it down, then you've got your finished shape, but then you can heat it up and do the whole thing again, reform it to something else. Whereas the thermoset, once you've formed it into a shape, basically that's the end of it. That's it. Thermoplastic lends itself nicely to recycling, because you can grind it up and have another go at using the material, whereas thermoset's not quite that simple. Then if we give you some examples of thermosets, which we will give some examples of thermoplastics, or polypropylene, PVC, acrylic, nylon, high impact polystyrene, polyethylene, PET, and then TPEs, thermoplastic polyurethanes, which are injection moldable and more or less you will probably term them synthetic rubbers, but they allow you to process them like a thermoset, and there's some really good uses for these things. Now, thermosets would be polyester, vinyl ester, epoxies, phenolics, melamine compounds, and we give a list on our website to give you a simple overview of those materials and their general properties. And then there are the different processes that are used to produce the end product. Now, with thermoplastics, the most common one is injection molding. Injection molding essentially takes some pellets of material, they're pumped through a barrel under pressure, molten, and into a die, which is hot, and it's cooled down, part popped out, and then the whole process repeats again. Blow molding, you're basically taking some material and you're blowing it to a shape. Vacuum forming, you're taking a sheet of product and heating it up and then sucking it to the shape of the form. An extrusion, where you're just producing the same continuous shape, some connection with injection molding, where you're sort of pumping, taking some pellets, pumping it through, heating it and pumping it through a shape, and then just taking that shape out continuously to get the same cross section continuously, such as pipes and various mold extrusions for different shapes which are continuous. And then of course you've got in thermosets you've got things like laminating, where you may be spraying something up and putting glass fibre and whatever. Now we've got some examples of those on our website, some video examples where you can go and have a look at that and see roughly what's involved. So apologies to those who want some more details, but this is just a general run through of what plastics are about. Thank you.